Hello again, physics friends. We are taking a new journey. We spent a lot of time on special relativity and we talked a lot about how that theory kind of upended our understanding of physics. And now we are going to focus on quantum mechanics, which is equally important and perhaps even more bizarre. What we're going to learn in this class is that a kind of hallmark feature of quantum mechanics is interference. And we're going to see that this works with photons as well as particles. And we want to build some intuition for what it means for there to be quantum interference. And we'll start out by talking about more classical objects. And we'll look at the interference of waves, in this case, sound waves or light waves. So to be clear, the waves and interference that we're talking about today is not unique or specific to quantum. So this was understood in classical physics long before quantum mechanics was discovered and interpreted. But so why then are we going to focus some time on this if this is a class on quantum? Well, we're going to build intuition using these kind of everyday experiences and everyday objects that we've interacted with, like sound waves or light waves. And we want to keep that model of interference in our minds when we talk about the interference of particles. So just to make sure we're all on the same page, what I have here is an animation that I've taken from Dan Russell's website. If you search Dan Russell and Penn State animations, you'll find a huge collection of wave phenomena animations. Really beautiful work. So let's just play this simulation through and we'll talk through some features as we go, okay? So as this is playing, this is an animation of a so-called longitudinal wave in which the particle motion and the wave motion are parallel to each other. So in both cases, the particles and waves are moving left to right, or left, right, left, right. The wave is progressing to the right, but notice that the particles do not go all the way left to right, right? The particles are oscillating back and forth in a very restricted region of space. And I really like this animation for showing that you can have kind of bulk motion that's similar to but different from the little particle motion. Now, I want to be clear about something here that, the study of waves is a rich and beautiful topic, and you can go very, very deep into the study. For us, we just want to take away a few ideas of waves. And one of the main takeaways that we want to focus on is this idea of interference. So we are going to discuss waves only in as much as we need to understand what interference is. And the basic idea, which can be very simply stated, is if you have one wave and you have another wave and they interact with each other or overlap with each other, they can either reinforce each other or they can cancel each other or something in between. Okay, so what we're going to see is if you have sound and you add sound to it, you can end up with silence, for example. Okay, and this is relevant for particles and in quantum mechanics because you can have the probability of finding a particle increase or decrease if you add a new particle to the mix or if you create new pathways for that single particle to go. And we'll see that in a subsequent video. So as we talk about waves, the main takeaway point here is that waves interfere, and we want a way to talk about and describe interference. And so we basically want to go from a picture like this, which is actually showing real particles oscillating in a way that creates wave-like behavior, and we want to kind of make a more schematic or abstract way to describe it. So the next thing we want to talk about is how do we draw waves in a way that's helpful to us when we think about the interactions of waves. So let's look again at this animation and let's point to some specific features, right? So we see the particles highlighted in red, or a few of them anyway, highlighted in red, are oscillating back and forth. But this wave itself, which is the region of high density of particles, is propagating rightward. Okay, so when we talk about and want to describe the motion of a wave or the properties of a wave, it's this kind of overdensity and where it is as a function of time and space that we'd like to capture in our schematic diagram. So we're going to focus on this part here, the wave that's traveling. Okay, and if you notice, there's, in this case, for this is this longitudinal wave, which could be, for example, a sound wave, you'll notice that there's regions of high density and then the regions of low density in between. So one way that we could capture and describe more schematically a wave is by plotting, say, the density of particles as a function of position, or the density of particles as a function of time. So now let's try to draw a schematic representation of this wave. So instead of showing the whole animation and simulation, let's just take a screen grab of it. So that's what's here. And we see that there's a bunch of particles. There's overdensity, underdensity, overdensity, underdensity, overdensity, underdensity. So there's this repeating pattern of increased and decreased density. And so let's try to draw this out schematically in a graph. Okay, so here's a set of axes. Okay, and the plot is the density of particles as a function of position, left to right. Okay, and I've added in this line called average density, which is this dashed line horizontally. And that is, recognizing the fact that, yes, there's overdense regions and underdense regions, but if we averaged over all of those regions, we would have some average density of the gas or the sound of the air, okay? So in this case, that literally would just be like count the total number of particles in this whole image and divide by the size of the image, either length or area or something like that. And that would give you an average density number. And then we're going to make a plot of the density as a function of position relative to that average. And in our minds, I'm making a one-dimensional plot because if you go up and down, you don't see any variation, right? So if you're in an overdense region, if you go up or down from there, you're still in an overdense region. If you're in an underdense region, if you go up and down from there, you're still in an underdense region. So what I'm doing is I'm kind of collapsing this picture vertically to get a single one-dimensional plot of the density of particles versus their position. So it looks like here I have like in this location I have an overdensity, and then again here I have an overdensity. So I would put, say, a dot right around here, and a dot right around here, and a dot right around here, and a dot right around here. And again, just to be super, super clear, these are my overdense regions that line up with the overdensities in the picture. I'll do one more. Okay. And then I'm going to have my underdense regions. I'll do purple for underdense. So here are my underdense regions in purple. So I'll put a dot there in my graph. And then I'm going to just kind of, in some region, somewhere in there, there's your kind of average density. I'm just going to eyeball this, right? And it's going to drop and rise and drop and rise and drop and rise. And I've drawn this kind of like a sine wave or periodic function. The exact profile might be hard to extract from the diagram, but it will look something like this, right? Where there's an overdensity that decreases down to an underdensity, and that cycle repeats. So this schematic representation of a wave is useful. It's easy to draw, it captures the main ideas, and has many uses, right? Let's introduce some notation and some terminology. When we have a peak, we'll often call that the crest or the peak of the wave. So that's where the density is the highest. And we have several examples of that. And then in contrast, if we have a region where the density is very low, we'll call that the trough or the minimum or the valley. So we might say things like, let's find where the crest meets the valley, or let's find where the crest of one wave overlaps with the valley of another wave, or where the peak of one wave overlaps with the peak of another wave. That's what we mean. And really for our study of waves, we just kind of need to know where we need to identify crests and troughs or peaks and valleys. And we just need to figure out like when one is lining up with another. Or if we have two different waves from two different sources, what is their overlap going to be? Is it going to be crest with crest? Is it going to be crest with trough, and so on? There are times when even this picture is even too complicated and we want to simplify things even further. So in the next slide, we'll introduce an even more simple and schematic representation of a wave that just highlights where the crests are. So a common way to draw waves is just to put vertical bands in the region where there's a peak in the density. Something like this. Okay, and you can see how that comes about. It's just a simplified version of the actual distribution of the particles. In this representation, we don't show the trough, but the trough would be midway between the peaks. So this would be the trough or the valley, but that's not shown, at least not explicitly. So when you look at this diagram, the lines represents the high density, and then midway between the line is the lowest density. In case you're wondering, there are other kinds of waves too. We looked at sound waves, which were longitudinal wave, meaning the particles of air oscillating back and forth in the same axis that the wave is propagating. But you can have a wave propagate, say, to the right and have the motion of the particles up and down. That's called a transverse wave because the motion is transverse or perpendicular to the propagation of the wave. So here's an example of that. So we have this wave that's the black propagating to the right, and that red point represents one particle. And notice that the motion of that one particle is straight up and down. It does not move left or right at all, even though the wave is propagating to the right. So this could kind of be like, imagine a floating cork or bobber on a lake or on an ocean. As a wave propagates by, that bobber would kind of move up and down, but wouldn't necessarily translate much left or right. This is also relevant for light and photons. So photons are basically an electromagnetic field, and we can represent the change of the electric field strength as oscillating up and down, as in high strength, low strength, high strength, low strength, as a given location in space, as the wave or as the light is propagating left to right. So this red dot, in the case of light, this red dot would represent the strength of the electric field at a given location in space. It would be going high, low, high, low, high, low, as a photon moves to the right. So the black sine wave represents like a photon passing through space and creating a disturbance in the electric field that oscillates high, low, high, low, high, low, and so on. Again, a lot of this is maybe more than we need to know for the purposes of wave discussion and quantum, but I think it's helpful to hear more background than less. So now I want to come back to this visualization of waves, right? We had this model where we said if we just draw a line that represents the peak or the maximum of the wave, and what we're not drawing is the valleys or the troughs that are midway between these lines. In the past, we had drawn just vertical lines that, in here we have a source though that's emitting a wave in all directions. Okay, so we're drawing actually half of those directions. It looks like it's just emitting to the right. It's not emitting over on this side. But coming out from a source, we now have these waves that are propagating outwards. What we see here is just a snapshot in time showing the, if this was a sound wave, this would be showing the air density as a function of position in this two-dimensional plot. Again, at a single time, but at all space. Okay, and in a minute we'll see why drawing a wave in this way is helpful. And just for reference, this is a snapshot of a simulation at ophysics.com, which has a great collection of waves and other waves and other phenomenon. Okay. So there's not much new here. We have a source and we have peaks of our waves coming out of that source. But look how this way of drawing the waves is very useful when we have two sources, because that way we can visualize how those two waves will interact. Okay, so this is the same simulation from before. Here I'm just again showing a screen grab of it. And now I have two sources, and they're separated by some distance d, and they're each putting out waves in these spherical wave fronts, or in this case, circular wave fronts. But you can see that there's this kind of grid-like pattern where the peak of one source wave intersects with the peak of another. You get these intersections, okay? And what we're going to see, so for example, if we take this arc from source 1 and we look at how it intersects with this arc from the other source, right? Like so. This allows us to get a sense for where the overall signal will be the strongest. And it turns out that when one peak aligns with another peak, those peaks add together and you get a peak that's twice as big. And if two valleys align with each other, you get a valley that's twice as deep. And if a peak aligns with a valley, then you get nothing, right? The valley and the peak will just cancel each other out. So this is kind of demonstrated visually here. On the right side, we have a screen showing the intensity of the wave as a function of position along the screen. And if we look at a region like here, where we have two peaks intersecting with each other, okay, so we have like the peak of one wave intersecting with the peak of another wave, and at that location, we have a very bright region. Okay, and the same is true down here. We have another peak interacting with the two peaks are interacting at that location, and notice that our signal is the brightest there. In the in-between regions, we have kind of a dark region here, okay? Well, that's where the peak of one is aligning with a valley of another, okay? So if you look midway between two peaks, that's a valley, and this is a peak. So we get this dark region here. For me, it's easier to see where the peaks line up because you actually have a line that's drawn where the peaks are. The valleys are just the absence of lines, so that's a little more tricky. And you'll notice, and we'll come back to this in a future video, but you'll notice there's this kind of pattern where it looks almost like light rays coming out in this pattern. And along those lines, you have constructive interference where you have these lines of constructive interference where the peaks are aligning with each other. So like on these dots, you have peak aligning with peak, like so, all along these bands. And so you get constructive interference in those regions and destructive interference in between. And these lines extend out to the screen on the right, and where they hit that screen is exactly where the light is the most intense, or the signal is the strongest in those regions. And we'll talk a little bit about more how this arises in a future video. But for now, we just want to know that we can draw schematically peaks of waves and then use that as a tool to figure out where one wave is interfering with another. When the wave from one source interacts with the wave from another source, you can get a reinforcing effect where the two waves add together and enhance the signal, or you can actually have a cancellation effect where the wave from one source cancels the wave from the other source, and that could be a full cancellation or partial cancellation and so on. So we call these kinds of interactions, we call this interference, which sounds like a bad thing, but is not necessarily a bad thing. Um, and and we can have constructive interference where a signal is enhanced, or we could have destructive interference where a signal is reduced. So let's take a look at some examples of constructive and destructive interference. We'll start with constructive interference, and here we have two waves. Red and blue are the input waves, okay? And so if you'd like, you can think of this as being like the density of air as a function of position. So high density, low density, high density, low density. And if you have two sources of these sound waves and they combine in a certain location in space, then we just add one to the other and we see what we get. So here, if we called this like 0, 1, and -1 for the red, excuse me, maybe I should draw that in red. For the red scale, so 1, 0, and -1. And then in blue, it would be 1, 0, and -1. Then here we have 0 plus 0, which gives 0 in pink, or purple I'll make it. And when we're down here, it's -1 added to -1 gives me -2. 1 plus 1 is 2, and so on. So the pink is literally just the sum of red and blue. And we see that the pink signal is bigger than either the red or the blue, and that's because a peak is aligning with a peak. So we have a peak here, we have a peak here, and that gives us an enhanced peak in the sum, okay? So we call this constructive interference because the signals added together are enhanced. Similarly, we can have destructive interference as shown in this diagram. So here we have our two waves, again the red and the blue are the inputs, and we're adding them together, and we can see that where there's a peak in red, there's a trough or valley in blue, and where there's a valley in red, there's a peak in blue, and the two curves are exactly added in a way that cancels out. So in this diagram, to be fair, the red and blue are slightly shifted left, right relative to each other, so that leaves a little bit of residual oscillation in the sum signal. But it is possible to have the sum be exactly 0 if the red and the blue were perfectly lined up. Okay, so again, 1 added to -1 gives 0. -1 added to +1 gives 0, and so on along the way. And we would call this destructive interference because if you think of it, if you imagine this is like the sound from a speaker and this is the signal from another speaker, we're adding together two signals that have volume, that have power, and they sum together to give silence. And we'll call that destructive interference. Indeed, this idea of destructive interference is exactly the technology that's used in your noise-canceling headphones that you may actually be wearing right now, right? So the basic idea, right, is you have some source of noise that you want to eliminate, and in order to eliminate it, you create anti-noise. Anti-noise is the same signal as the noise, but with a -1 multiplied by -1 to basically flip the sense of the signal. And when you add those two things together, you basically get no noise coming out. So this is built in a way that's built into your headphones, and this picture kind of goes right to left. So you have input sound from the environment, which is the red signal, and there's a microphone that listens for that sound. In real time, it creates the inverted version of that signal. So where there's a peak, there's a trough, and so on. And that's created by a speaker and some processing electronics. A technical term for this is 180-degree phase shift. That means just shifting the signal by half of a cycle. And in doing so, you have red and green signals that are essentially perfect versions of each other, but one is minus the other, such that when you add them together, you get a flat line signal, which is quiet in the context of sound. So this is basically all we need to know, is that waves can add together in a way that reinforces the signal or that destroys the signal. And we'll see that in quantum. This applies to light. This also applies to particles, which have wave-like behavior as well. As a way for you to get direct experience with constructive and destructive interference, I'm asking that you go to this website, falstad.com/interference, where there's a simulation of the interference of waves from two different sources. Okay, what's drawn here is kind of a visual representation of that interference, where white means high intensity and black means low intensity. And the way it's configured now, we have two sources and they're emitting a signal, a wave-like signal. And in certain regions, you get destructive interference, and in other regions, you get constructive interference. But the beautiful thing about this this simulation is that when you run it on your actual computer, you can listen to the interference with your ears. Okay, so what does that look like? Well, imagine this is us, and I'm using a Mickey Mouse symbol here because he has big ears and they're far apart, so we can think about that as our own ear. So imagine we are Mickey Mouse in this diagram, and the sources are speakers, and in particular they are the speakers on your laptop computer. Okay, now the sound is coming out of those speakers, traveling through the air, and to be clear, you cannot do this with headphones or earbuds. You need actually the audio signal from each speaker to interact when it reaches your ear. So if you use headphones, then the signal from one speaker basically is going into one ear, and the signal from the other speaker is going into the other ear, but there's no chance for those two signals to interact. Okay, so here we are, Mickey Mouse. We have a left ear and a right ear, and notice that the left ear is in a region of blackness. That's where it would be silent or quiet. And the right ear is in a region that's green. That would mean a stronger signal. So by having one ear in the quiet zone and one ear in a louder zone, that actually makes it harder to detect this interference signal because your brain kind of adjusts for the two. So what we'd actually like to do is block one ear so that we only are listening in one place at a time. Okay, so here we go. I've covered up one of Mickey's ears. So when you do this experiment, just put a finger in one of your ears to block that ear, and then your other ear is a sensor that's in one place at a given time. And as you play the sound out of your speakers using this simulation, move your head side to side, okay? So that's Mickey moving this way and that way, and you'll go from a region of quiet to a region of high sound, high volume, to a region of quiet, and so on. What you're going to find is that this midline in between your two speakers on your laptop will be the loudest. And then depending on the specific frequency that you play, you might have to travel a long way or a short way to go from loud to quiet and then back to loud again. So go have fun with this. It's a really interesting simulation, and let's see what you can see. You should be able to hear this interference directly with your own ears. The other activity I'd like for you to do is to view another linked video, which shows a dog that I came across when I was walking on campus last year. This dog must have been running hard, and he jumped in the water and was sitting there completely motionless, except for his rapid breathing. And as he breathed, the sides of his bodies were opening and closing, or expanding, contracting, and that was creating ripples in the water. And the really cool thing about it, though, was that different parts of his body were creating different signals. So it's almost like in the previous example, on the previous slide where we had two sources of sound and you could see how they interfered, where here he had many sources of water vibration around his body, and the pattern in the water looks very similar to what we were looking at in the previous page, including the fact that there's interference, that there's regions where the water level was higher and there are regions where the amount of ripples was less. So I have an activity for you where I'd like for you to view this video, take a screen grab, and identify constructive interference areas and destructive interference areas. And also you get to look at a good old doggo in the meantime. Okay, so that's it for our overview of waves and interference. Going forward, we will tie ideas of interference in waves to quantum mechanics, and that's coming up next.